my phone.
Yes, you may. If that's what you need to do, do what you need to do. Okay, guys, let's do some pre-cal. Sorry, I know, we're all distracted. It's a Friday. I'm with you. It's been a whirlwind of a week. So, let's finish these notes and get this 2-3 out of the way. Okay? We are on the last page of lesson 2.3. And so we are talking still about zeros, which is if you look back at the last problem we did, we started finding zeros. And the first one we did was finding zeros of the polynomial algebraically. So we set the equation equal to 0, and we used our algebra solving skills. Okay. So we're going to start looking at graphically on this next page. Now, there is a bunch of information here to kind of look at. So let's read through this information here, and I'll explain it and make sense of it in example 5. First of all, it is possible to have what we call repeated zeros if the multiplicity of a 0 is 2 or greater. Now, when we talk about the multiplicity of a 0, so first of all, remember a 0. Like, for instance, if you look back to the last problem we did. And she's already packing up. Are you ready for my student that's marked virtual but sitting in my class? Okay. I'm sending her. She packed up as soon as the phone started ringing, so she knows. Okay. Bye. So FYI, Barb never said a name, but you know.
She knows who she is.
Yeah, pretty much.
Yeah, that's fair.
Okay. There'll be a video on Schoology later, Maggie.
Okay, that's fine.
Might even be this video that I just talked to you in.
We'll see you in 2 weeks. Bye, see you, Stella. Bye.
Okay, guys. And there are 5 remaining. Okay. So what I was saying, it's possible to have what we call repeated zeros. If you look back to the problem we did at the bottom of yesterday's homework, we had factors of x, x minus 3, and x plus 2. Each of those factors occur once because they each have an exponent of 1. Okay, so now a repeated 0 is if the multiplicity is 2 or greater. When we talk about the multiplicity of a 0, we're talking about the exponent on the 0. Okay, let me get that where you guys can see it. That's helpful, huh? Okay, so we're talking about the exponent on the 0. So, for instance, if you have a factor like x minus 3, but it's x minus 3 raised to the power of 2, that affects the 0. That affects how our graph touches the x-axis. And that's what we're talking about here, is how the graph touches the x-axis. Does it just cut through, or does it touch it and go back up? Okay? So, this occurs if something can factor down into a quantity squared, cubed, etc. The example here, x cubed plus 4x squared plus 4x factors into x times x plus 2 squared. So, this x plus 2, which would be a 0 of negative 2, that would have a multiplicity of 2 because the exponent is 2. Now, when you have that even multiplicity, what happens is instead of your graph simply crossing through the x-axis, the graph might touch the x-axis instead of crossing through it. So when I talk about touching the x-axis, notice it says like the W or a parabola. If a parabola just comes down and touches the x-axis and goes straight back up, it's touching it. It's not crossing through it. Okay, so if the power on the factoring, so called the multiplicity, is even. So if you have powers of 2, 4, 6, 8, whatever the case is, the graph will simply touch it. So it'll touch it and go back up, or touch it and go back down. If the power is odd, so your traditional 1, or even odd powers of 3, 5, 7, so on and so forth, the graph will actually cross through it. Both are still considered zeros, okay, in that they intersect the x-axis. So they're still considered zeros. Sorry, I'm going to turn the volume down the TV so when emails and stuff come through, they don't be obnoxiously loud. Guessing that was an email at least. Okay, so let's look at example 5, and I'll try and explain exactly what I mean and show what I mean, okay? Okay, so example 5 is asking several questions. It asks us to state the degree of the problem. It asks us to list the zeros of the problem. The problem is this f of x. It's also asked us to state the multiplicity of each zero, and then whether the graph crosses the x-axis or touches. Okay? And then we're also going to sketch the graph when we get done. In the end, I'll be honest, I'll show you the graphing calculator example, but I want to talk about how we can kind of do a sketch by hand without ever using the calculator. Okay? So, let's see. Where do I want to begin? Let's begin by moving this up so my virtual can still see. Okay, so first thing they asked us for is a degree. I want to know the degree of this problem. Now, what do I mean degree? The power. It's the highest power when the problem is in what form? Standard form. Okay? Now, this is not in standard form, is it? No. Standard form would be all multiplied out. Good news, you don't have to multiply it out. But look, if we multiplied this out, what would end up being the highest power? What? 5? Why 5? Because there's here, x plus 2 to the third would end up with an x to the third. X minus 1 to the second would end up with an x to the second. And an x to the third times an x to the second is going to be an x to the fifth. So the degree of this problem is 5. Okay? And that's because it would be an x to the fifth. Now, what does x to the fifth mean about the shape of this graph? Because we're going to sketch this eventually. So we talked yesterday. It has an odd degree. What does that mean about end behavior? And you can use Algebra 2 terminology for this end behavior if you want. But if there is an odd degree, choices, down, up, down, down, up, 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 down. What's it mean if it's an odd degree, and what type of, is this going to have a positive or negative lead coefficient? Positive x's times positive x's is going to make it a positive lead coefficient. What's that say of those choices? What kind of end behavior? She says up, down.
Is that wrong? Because you're really thinking about it.
I know, I did have to stop and think, I'll be honest. She said up, down, and I stopped to think. Okay, so since it's odd, let's go with that. Since it's odd, what's odd eliminate? It eliminates up, up, and down, down. So that gives me up, down, and down, up. Now, since it's positive, I'll be honest, I do disagree. So it's down, up. Since it's positive, that means it starts low. Kind of think like an x to the third, and ends high. And what does a positive x to the third look like? It starts low and ends high, right? So that right there, because it's x to the fifth, that's going to be what the shape of this graph looks like. Okay. Let's see. We talked about the degree. It also asked us to list the zeros. Okay, what are the zeros of this problem? Negative 2 and 1. Can we agree to that? Okay, negative 2 and 1, because x plus 2 equals 0, gives me x equals negative 2. And I'm going to space them out because I'm going to write some information below them. And x equals 1 comes from x minus 1 equals 0. So those are my zeros. Yes? Okay. Next thing we're going to state is the multiplicity of each of those zeros. Now, if you remember from up top, how do we find multiplicity? What are we looking at for multiplicity? Not the graph. Okay, the power on the factory. So the 0, x equals negative 2, came from x plus 2 raised to what power? The third. So the 0 of negative 2 has a multiplicity of 3. We'll talk about what that means in a moment. What about my 0 of 1? X equals 1. It comes from x minus 1 to the second, and so what's the exponent there? And that is 2. So we have zeros of x equals negative 2 and x equals 1. X equals negative 2 has a multiplicity of 3. X equals 1 has a multiplicity of 2. Now, okay, I talked about it earlier. Because negative 2 has a multiplicity of 3. Is 3 even or odd? Okay, so 3 is an odd multiplicity. When the multiplicity is odd, are we going to cross through the x-axis or touch the x-axis? If you go back and read up above example 5, when the multiplicity is odd, the graph is still going to cross through the x-axis. So this is going to cross through the x-axis at the 0, x equals negative 2. Okay? Then, we had 0 of 1. The 0 of 1, maybe I should zoom this in a little bit so we can see a little bit better. The 0 of 1 had a multiplicity of 2. What does an even multiplicity say? It touches, which means it's not going to cross through. It's just going to touch at that 0. So this means our graph is just going to touch at x equals 1. I'm trying to use arrows to try and connect my thought process here. Okay? Because I want you, later if you just look at it and say, it crosses, it touches, why? This is what I'm trying to connect for you. Now, before we graph it, I got one other thing I wanted to find. And it didn't ask it for it. I can't remember if this was in Algebra 2 or Pre-Calc the other day we talked about it. Oh, it was in Pre-Calc. It was at the beginning of this lesson. I remember it. Another easy thing to help with the graph is your y-intercept. Remind me, how do I always find a y-intercept? I couldn't understand what you said.
I don't think it's right, so I'm not going to repeat it.
How do we always find a y-intercept? Y-intercepts occur when x equals
0.
0 every time. So the other thing we're going to compute real quick before we sketch this graph is the y-intercept. And I say the y, I compute it because it's not actually given in this equation. So the y-intercept means we're going to find f of 0. So when x equals 0. So if I find f of 0, 0 plus 2 cubed times 0 minus 1 squared. Zero plus 2 is 2. 2 to the third is 8. 0 minus 1 is negative 1. Negative 1 to the second is positive 1. 8 times 1 is 8. So we have a y-intercept of 8. Okay, now, I'll check myself on the calculator later, but we're going to graph this, just using what we've talked about here. So not using the calculator yet, but just using the information of what we've talked about. Now, knowing what I know about this graph and how I'm going to draw it, I'm going to draw my x-axis lower because I don't really need room below it. And there's my y-axis. Okay. Important points. Well, I know I have zeros of -2 and 1. And I know I have a y-intercept of 8. So those are important points on my graph, correct? Now, trying to zoom this in a little bit, but leave pertinent information up here. Couple of things here. End behavior. We decided our end behavior was down and up. Meaning on the left side of my graph is going to be down. On the right side of my graph is going to be going up. I just drew that in pencil, but that's just what my brain's thinking. You don't even have to draw it in on your graph ahead of time if you don't want. But you've got to have your brain thinking, okay, I know my graph has to start down here and end up here because it was a positive x to the 5th. Okay? Then, we know we have zeros at where? Zeros at -2 and 1. So I know my graph has to somehow touch the x-axis at -2 and 1. Now, what specifically is happening at each of those zeros? What specifically is happening at -2? It's doing more than -2 because it has an odd multiplicity. It's actually going to cross through. I'm just going to kind of put a C underneath that as my physical reminder that, okay, my graph is going to cross through there. What happens at x equals 1? It's an even multiplicity, and so my graph is just going to touch, which means if my graph is on top at that point, it's going to come from above and go back up. If my graph is below at that point, it's going to come from below and go back down. Depends on the situation. And what's the other point I know? Y-intercept of 8. Okay. We have enough information to draw a sketch of this graph. It's not going to be perfect, but it's a sketch. You ready? Okay, my graph starts where? Down here. We're going to do what at -2? Cross through. Now, I will tell you, because the higher the multiplicity is, the more my graph flattens out. So instead of just fully crossing through -2, it's going to kind of flatten a little bit before it continues up. I don't know if I did a great job or not there, but it's going to kind of flatten a little bit before it continues up. So it crosses through at -2.
Wait, why is it flat?
It flattens, the higher the multiplicity is, the more it flattens out. If this is just a multiplicity of 1, it just crosses through. But the higher the multiplicity get, it kind of flattens more. Okay, so we cross through at -2. Where's the next place I know I have to go?
8.
We have to go up through 8.
And then start to go down to 1.
Okay, and we don't really know if 8 is our max. This is one of those things we're just sketching it. 8's going to kind of end up being my max, I'll be honest. I don't know that it is. But then the thing is, we have to go down and hit where next? 1.
We gotta go back up because you just touched it.
What do we do at 1?
Bounce back up.
We touch, and so that means we're going to bounce back up. I like that vocabulary there. We're going to bounce back up. Because does that also match my end behavior?
Yes.
Yeah, because my end behavior says that this graph ends up going back up. Now, I did that without looking at the calculator graph. Now, to be honest, is my calculator graph going to be exact?
No.
No. But the idea is, am I going to have the same shape?
Yes.
And that's what we're looking for here. So, oops. Good news is,
We can't even see that.
okay, I'll fix it in a moment. Let me get it typed in here. X plus 2 to the third. X minus 1 to the second. Let me get it so where it's visible.
It looks the same.
I'm going to do a zoom 6 because, yeah, who knows what I last graphed.
Beautiful.
Yeah, I got the same type of shape.
Perfect.
Now, if I look closely at that, I'll be honest, I can tell my max is not at 0.8. If I look closely, it looks like my max is slightly to the left of 0, because it looks like it's slightly to the left of the y-axis. But again, this is just a sketch, and that's what I'm looking for. Okay, the sketching is probably going to be something that's a little tough for you guys still at this point, but I want you to work on thinking these things through. Okay. Questions from anybody on this? Virtual or physical? Okay. That's probably the hardest thing we're doing today. We got 2 more examples. Okay. Hopefully you guys have copied down what you need copied down. Okay. So notice right before example 6, it gives us a hint. Sometimes you have to look closely to tell what is happening, like by zooming in. So that's your hint of how we proceed on this next problem. Notice example 6 is zooming to uncover hidden behavior. Okay? It says find all real zeros, which real zeros just indicates zeros that you can physically see on your calculator. We'll talk about non-real zeros in days to come. But right now, we want all real zeros. Now, what do I mean all real zeros? Where are we going to find those? On the graph, those are my what? X-intercepts. Could I do this problem algebraically if I wanted to? Yeah, the answer is no. There's decimals and stuff. This doesn't factor. Besides the fact we're in a graphing section. So what do? Plug it into the graph. I would encourage you to try this on your own. It's good practice. Gosh darn it.
Oh, you messed it up.
I did. I didn't get out of my exponent. You guys all know what that's like.
Yeah.
I didn't. I just cleared several characters, but I should have just cleared the whole thing. It would have been just as easy. Okay. As always, I'm going to start on a standard Zoom screen. Now, can virtual see my graph at all? Oh my gosh, with you guys all being here. Okay, good. Okay. Okay. You got the basic shape of the graph? Okay. Do I need to zoom out to see the rest of the graph?
No, not really.
Not really, because what are we looking for? X-intercepts.
We do need to zoom in though, right?
Okay, so the question is, yeah, should we zoom in maybe?
Yeah.
I mean, here's the deal. Can you tell me right now how many zeros this problem has?
1, 2, 3, 4, 5.
4 or 5.
Look.
Okay, so thus the reason we need to zoom in. Because here in class, I've heard 3, 4, and 5 as possible numbers of zeros. Okay? So this is why we need to zoom in. Because it's hard to tell. Now, if you want, could you go ahead and find that one that's by itself? Let's go ahead and find the one that's by itself. Meaning, this one that's over around -3. Okay.
Yes.
How do we find a zero? On these calculators, recall we do a second calc, And to find a 0, which is an x-intercept, you go to number 2. Remember, it's asking me questions. Left bound. That means I need to go left of the x-intercept I'm looking for. So, and I'm choosing to do this before I zoom in because I think it'll be a little easier, which means I need to go above that -3 intercept. Hit enter. Right bound means I need to be to the right of it, which happens to be below it. And then for my guess, the way mine is set up, I can't really, my guess is just right where I'm at because I can't really get there. Okay, what is my first 0? And I have 2 decimal places, which is -3.1. Now, okay, this is a good teaching moment. My y value came up as -6e -12. What is that equivalent to?
0.
That is 0.
I saw that in my homework. I just ignored it.
Yeah, that is 0, folks. Anytime you see that e with a negative number following it, it's equivalent to 0. It's a whole bunch of 0.0000000 point or something. It's 0. Okay? So my first 0 is x equals -3.1 or -3.10. Okay, now that's 1 for sure. Over on the other side, some of you have zoomed in, you've probably seen. We've got how many more to find?
3 more.
3 more. My recommendation, what's a good zoom tool to use to see that? Okay. Levi has latched onto the Z-Box, and that's a good thing. Z-Box would be perfect right here because I can zoom in specifically on what I need. So I'm going to go zoom. It's number 1. And remember, you're drawing a box around what you want to zoom on. So I'm just going to focus on this section right here. Hit enter at one corner, and then draw your box to a diagonal corner. And I just want to see that section that goes from like 0 to 2, basically. I'm going to hit enter, and it's going to zoom me in. And the reason this is so important is because now can you easily find your zeros. You're not trying to get a left and right bound when you can't even see what's going on. Okay? So, find your last 3. I don't know, how much of this do I need to do? Okay. So if I'm just going to go in order from left to right. So it looks like this is around -1/2, positive half, so to speak. Left bound, so I'm left of it. Right bound, so I'm right of it. And into the center. Okay, it's more than around 1/2. It's exactly 1/2, isn't it?
Yeah.
0.5. So we have 0.5. Continue along. Repeat the process, right? Let me know when you get another one.
$1.1 and $1.37.
1.1 what?
It's 1.133, so it's just 1.1.
Well, if I'm going 2 decimal places, 1.13.
Oh, yeah. And 1.37.
What's the last one?
1.37.
1.37. Okay. So what I was doing here is just putting some notes down. I'll leave this up on the screen. First of all, over on the left, I just wrote reminder notes that I use Z-Box here to zoom in and see that section. And then I use second calc 0 to find my zeros. And hey, maybe by this point you guys are getting proficient enough, you don't need those reminders. You know what to do. But if it's going to help you, write them down. I have 4 solutions here. Negative 3.10, 0.5, 1.13, and 1.37. And then off to the right, I just kind of sketched a graph. And I showed in that graph, I just kind of sketched it, and I'm showing that those are the zeros, right? They're the x-intercepts. My goal is anything to help you guys remember how to do this when you're doing it on your own, right? Bless you. Bless you.
No, I'm
You're
right
out
here.
You're out here.
Yeah, Rona, I gotta go.
If every cough or sneeze or anything meant anything, we would have been shut down from day one, I mean. Questions on this example? I like the graphs until we get a funky one that, makes it really hard, but I like the graphs.